Okay, class. So we're going to start a new section, common ion effect. And they also write common ion effect as CIE. You'll see me writing it that way. Okay, now, before we talk about common ion effect, I need you to remember what we talked about in last chapter. We talked about a strong acid and bases, and we said what that means to be a strong acid or base. You would fully dissociate. You completely would break up in water. You would ionize, break up in water 100%. An example is hydrochloric acid. 100% breaks up into H plus and Cl minus. And don't forget, the H plus is what makes something to be acidic. And the strong acid, you would have to memorize. These are the list of the strong acid. Everything else is considered weak. The strong bases, if you have 1A group or bottom of 2A group, those would be considered strong bases. And the bottom would be SR, BA, and RN. Those would be the strong bases. Okay, now, what does it mean to have a weak acid or base? Weak acid or base, they will only partially dissociate. They would not fully break up. For example, hydrofluoric acid, some of it would break up, but most of it would stay together. So that's what we talked about last chapter. Hopefully you remember that. So for example, here, if you have 100 hydrofluoric acid molecules, probably 95 would stay together, and then 5 of them would break up. Now let's start this new chapter. And some of it still review, which is great. The more review we do, the better it is. Let's talk about acetic acid. Acetic acid is a weak acid, okay? Now, what I want you to do, take a minute and write the formula for acetic acid for me. Write the formula for acetic acid for me, hopefully without looking it up. Okay, hopefully this is what you have. You have an H at the beginning and C2H3O2. There is another way that is very common to write acetic acid, and that is CH3COOH. Especially when you go to organic chemistry, this is how they would write acetic acid, CH3COOH. So both are right. Because if you look at over here, 1, 2 carbon, so 2 carbon, and then 3 hydrogen, 2 oxygen, and the acidic hydrogen. But this is a more sophisticated way of writing. Now, in this way, CH3COOH, this would be the acidic hydrogen. More sophisticated way of writing. If you want to impress someone, this is how you would write acetic acid. Now, I need you to remember that we said every time we have weak acid or base, and I want to write it down because I want to make sure you really understand this before we move on. Every time we have weak acid or base, we will have an equilibrium. We would have an equilibrium, and we would need to do a hydrolysis. Hydrolysis when you add the water to the acid and base and then see what happens. So every time you have a weak acid or base, you have an equilibrium. Do a hydrolysis and you have a Ka or Kb, right? You have an equilibrium constant. Okay, now let's do a hydrolysis for acetic acid. If you do a hydrolysis for acetic acid, so CH3COOH, so you want to do a hydrolysis for acetic acid, is a weak acid plus water, weak acid, equilibrium, double arrow. So what I want to do a hydrolysis for acetic acid, is a weak acid. So I want to add it to water, so double arrow, because it's a weak acid, it has equilibrium. And remember what we talked about, and I need you to really remember that. We said acid would lose a hydrogen and base would get the hydrogen. And water is a base here because water could act as an acid or base depending on the situation. And since acetic acid is my acid, water would be my base. Acid is going to lose a hydrogen, so I'm going to end up with CH3COO minus, because remember what I said? I said this one right here is the acidic hydrogen. This is the acidic hydrogen. And my other product is water gets the hydrogen, is hydronium. And also don't forget that the charges on both sides are equal. Plus and minus ends up being neutral, and this is also neutral. I'm going to write this down one more time because I need you to really remember it for me. That acid would lose a hydrogen and base would get a hydrogen. Remember that. Remember that. Remember that. All right, so that's a good review of what we've talked about. Now let's go over what this chapter is all about, and you need all this information. Now let's talk about common ion effect. What common ion effect is, basically there is a shift in equilibrium. There is a shift in equilibrium caused by the addition of an ion that is part of the equilibrium. And when I say addition of an ion from a different source, you would add it. So in the shift in equilibrium, if you add from a different source, if you add one of the ions that are involved in equilibrium. And we've seen this before. You definitely have seen this before. So what are we talking about? Remember Le Chatelier? Yeah. So based on the Le Chatelier principle, the equilibrium will shift. And we did Le Chatelier a little bit last chapter. Okay, so that's a definition of common ion effect. But let's do an example to really understand what it really means and not just memorize the definition of what it is. So what I'm going to do, I'm going to rewrite my acetic acid hydrolysis. CH3COOH, my acetic acid, plus water is a weak acid. So I'm going to have an equilibrium with a double arrow. Acid is going to lose a hydrogen, so I have acetate now. Water is going to get the hydrogen because my base, I have hydronium now. Okay, so that is my equilibrium. Now, what are the common ions in this equation? What are the common ions? So, ions have to have charges, right? So, this is my common ion, and this is also a common ion. So, these two would be considered common ions. Now, here I have two questions for you. The first question: what happens if I add additional acid? And here's the second question: what happens if I add additional acetate? Okay, you can pause my video, I won't take it personal, and then answer these questions. So if I add additional acid, what am I adding? I'm adding hydronium. That's what makes something to be acidic. So if I add additional acid, which way would the equilibrium shift? I'm adding more of this, the equilibrium would shift to the left, so it could use up the hydronium to reach equilibrium. So if I end up adding more acid, which is hydronium, and hydronium is on my product side, it will shift to the left. It will shift to the reactant side, so it would to reach equilibrium, to balance equilibrium out. Now what happens if they add additional acetate? Acetate is right here. If I add additional acetate, the same thing. It will shift to the left, to the reactant, to balance it out. So if I add acetate from the product, again, it would shift to the reactant side to reach the equilibrium again. So these are my two common ion effects, and if I add more of this or more of this, the equilibrium would shift. So far so good. That is our common ion effect. Now let's do another practice for this. Let's say I have ammonia, which is a weak base. Okay, so this is ammonia. I do want you to know the name. So take a minute right now, and what I want you to do, write the hydrolysis for ammonia, because ammonia is a weak base, so you can write the hydrolysis for it. So I would have NH3 plus water. This is my equilibrium. It goes back and forth. Equilibrium because it's a weak base. The base is going to get a hydrogen. It becomes ammonium. Now water is going to be my acid because ammonium is my base. So acid is going to lose a hydrogen. I become OH minus. Okay. Now, here are the two questions. What happens if ammonium nitrate is added? And the second question I have, what happens if NaCl is added? So if I add ammonium nitrate, now you got to remember for me that ammonium nitrate in water is just ammonium plus and nitrate minus. Nitrate doesn't really do anything. It's just a spectator. It's not one of the common ion. It's a spectator. It's not going to do anything. But ammonium over here, it matches over here. It's a common ion. Nitrate doesn't matter. It's not even part of, nitrate is not part of this equation. But ammonium is part of this equation. So if I add ammonium nitrate, I'm essentially adding more ammonium. So it would shift to the reactant side to balance it out. So I'm adding more ammonium, it will shift to the left. Now what happens if I add NaCl? So if I add NaCl, again, what you have in water, you have Na plus, Cl minus. These are not part of the equation up here. These are not part of the common ion. If they're not part of the common ion, nothing is going to happen. Nothing is going to happen. Oh, what just happened? Nothing is going to happen. So that is our common ion effect. You have to have one of the common ion that is part of the equation, and then you do Le Chatelier principle. If you add it, you have to shift to the other side. All right, so far so good. Now, let's do a practice problem. Let's do our first practice problem. Here's our practice problem. Acetic acid, which is HAC, is a weak acid, right? Acetic acid has a Ka of 1.8. So acetic acid has a Ka of 1.8 times 10 to the minus 5. Okay? What I want you to do, I want you to calculate the pH of a 0.10 molar acetic acid solution percent dissociation. Okay, now let's do this one together. So I have acetic acid, which is a weak acid. If I have a weak acid, I'm going to write the equilibrium, which is HAC plus H2O goes back and forth into AC minus plus hydronium. You know how to do this by now. Okay, again, I just abbreviated HAC. It's the same thing. This is going to lose an H, so this is acetate. This is going to get a hydrogen. All right, now because this is a weak acid, and remember from last chapter, I have to do an ice table because I have equilibrium. At the very beginning, I have 0.10 molar acetic acid. I don't have any of this. Minus X, X and X. My equilibrium is 0.1 minus X, X and X. Again, weak acid, you know how to do this. And because this is a weak acid, is an acid, I need a Ka value. And I have a Ka value. My Ka is 1.8 times 10 to the minus 5. Again, equilibrium constant is product over reactant. Product over reactant, basically the concentration of acetate times the concentration of hydronium over the concentration of acetic acid. Liquid is not part of the equilibrium constant. Now, it would be X squared over 0.10 minus X. You can definitely assume this is 0 because our equilibrium constant is low, and whatever this number is going to be so small compared to 0.10. So if I solve for X, I get 0.0013. Now what does X mean? X is concentration of acetate. That doesn't do me any good, but is also concentration of hydronium. That does me a lot of good, because if I have the hydronium concentration, I can figure out the pH. pH would be minus log of hydronium concentration, which is 0.0013. So my pH is going to be 2.87. We talked about this in the last chapter, that here in this problem, I am limited to 2 sig fig right here. Okay, and for the sig fig, you have to, when you have log, you have to count it after the decimal place, because the 2 is basically because of this, and the 2 goes for that. So after the decimal place, that's where you have to figure out your sig fig. All right, perfect. Now, percent dissociation. Basically, percent dissociation means how much of this hydronium broke up, because hydronium is what makes something to be acidic, right? So that really matters, that how much of this hydronium broke up. Okay, now let's do that one together. So percent dissociation would be concentration of hydronium over concentration of acetic acid. Basically, how much of the acetic acid broke up. So we know at the beginning we had 0.10 molar acetic acid, and we know that 0.0013 broke up, right? Times 100, I get 1.3%. Not much, huh? Only 1.3% actually broke up. So when you have acetic acid is vinegar. So when you have vinegar on your salad, it tastes very vinegary, right? It tastes sour, even though there's only less than 1.3% dissociation going on. Small amount actually breaks up, right? So most of it stay together. Most of it is stay together. Only 1.3% would break up into this. Only 1.3% will break up, but it still is enough to have that sour taste. All right, beautiful so far. This is a really good question. Now, I'm going to consider this part A. And we're going to do the part B, and that's going to bring it home. Here's a question. Calculate the pH and percent dissociation of acetic acid, HAC, in a 0.10 molar. Let's see, calculate pH and dissociation of acetic acid in a 0.10 molar acetic acid solution and 0.050 molar sodium acetate, NaAC. Again, I'm just abbreviating. HAC, AC means acetate. HAC means acetic acid. Okay, ready to do this? So, we're still talking about acetic acid. I'm asking for the pH and dissociation of acetic acid in this solution. I'm still talking about acetic acid. So what I'm going to do, I'm going to write down HAC again. And it would go back and forth, equilibrium, AC minus, and this one, you already know how to do this. Okay, again, this is a weak acid. I have an equilibrium. I have to do equilibrium constant. I have to do an equilibrium constant. That hasn't changed. Okay. Now what I have in this solution, I have 0.10 molar acetic acid. But what else do I have? So I have 0.1 molar acetic acid, but I also have in the same solution 0.05 molar sodium acetate. Now check this out. We talked about this. So sodium acetate would be Na plus and AC minus, right? Would Na plus do anything? No, Na plus is not one of the common ion. It's not part of this. It wouldn't do anything. But AC minus, that's one of the common ion. Yes, it's right here. So it does have an effect on it. And how much of that do I have? It's a 1-to-1 ratio. So it would be 0.050 molar. So sodium is a spectator. It's not going to do anything. But acetate is a common ion. Minus X, this is 0 at the beginning, and X. So what I end up having is 0.10 minus X. I have X and X. Same thing as before. Nothing has changed. So I'm going to have a Ka value. The same Ka from part A I can use, which was 1.8 times 10 to the minus 5. Again, product over reactant would be product over reactant, which would be X in this problem, times 0.050 plus X over my reactant 0.10 minus X. Again, what I just did, all I did is just product. Oh, you know what I just, guys? I was trying to make sure you're listening. So here, it would be 0.05 plus X, right? Sorry for that. I was testing you guys. So far so good because I have this initially. So this is my equilibrium. Product over reactant. And I have this one too because in this solution, I also have sodium acetate. So I have some of the acetate also in the solution from the beginning. From the beginning, I also have that. Okay. So when I do this, now you can definitely assume again that this X is 0. You can also assume this X is 0 also. Because again, compared to that, it's going to be a tiny number. That makes it a little bit easier to solve. So then I have 0.050 X over 0.10. If I solve for X, what I end up getting is 3.6 times 10 to the minus 5. Again, what does X means? Anything good? Yeah, hydronium. I like the hydronium idea. Acetate doesn't get me anywhere. Okay, so that is, again, my hydronium concentration. So I can figure out the pH. The pH, whoop, what just happened? There we go. The pH is going to be minus log of hydronium. Okay, let me slow down a little bit, make sure you guys understanding this. Again, equilibrium constant is product over reactant. My product over reactant, I have some of the acetate, some of the acetic acid. I can assume these are 0. Not going to make much difference. This is a small number. These are going to be so tiny compared to that. So then these are 0. This times that. 0.050x over this. So the x is going to be my hydronium concentration. I can figure out the pH minus log of hydronium. If I do that, what I end up getting is 4.44. Now, let's figure out percent dissociation. Again, would be the hydronium concentration, how much broke up, which is 3.6 times 10 to the minus 5, over how much I had from the beginning, which was 0.10 molar. So I had 0.10 molar of the acetic acid, and this much of H3O plus showed up. So that's how much dissociated. And if I times it by 100, what I end up getting is 0.036%. That's very interesting, isn't it? So what happened here? Let's talk about what happened here. Part A, my percent dissociation was 1.3%. And part B, my percent dissociation went down to 0.036%. Why? Why did that go down? The reason it went down is because of common ion effect. That's what we expected to happen. Remember, here I have acetic acid. Going, let's just say H plus by AC minus. I'm just going to have it to less sophisticated way to get the point across. So when this was going on, the percent dissociation was 1.3%. Now I added a common ion, I added the acetate. So if I add the acetate, the equilibrium is going to shift to the left. So I have less of this going on. So the common ion makes the dissociation to go down because equilibrium is shifted to the left. So it shifted this way, so percent dissociation goes down. I have less of this now. I have less of this. Now, let's see what happened to the pH. Part A, the pH was 2.87. Part B was 4.44. Does that make sense? It does make sense. Because of the common ion effect, the equilibrium shifts this way. Now I also have less H+. Again, common ion effect, the equilibrium shifts to the left, to the reactant. I have less product now. I have less H+. And H+ is what makes something to be acidic. So now my pH is also going to be more basic. My pH is going to be more basic, and that's what I expected. So this is a common ion effect. Okay. Nice job. We'll do more practice problem on this later. Common ion effect.